So next we're going to look at polynomial models, specifically volume type problems. In number 3, we have a large plywood box has the following dimensions, where its length is 9 feet greater than its height, its width is 4 feet less than its height, and it is to have an open top. Now the open top doesn't really matter right now, but we will see open top box problems a lot throughout these notes. And that just means that there is no top, you can reach directly into the box. So we want to start off drawing a picture of a box and label the sides using x as its height. So I only know how to draw a box in one way. All of my boxes are going to look the same, but the picture doesn't really matter as much as just having a visual that would help you out. So here's our box, and we know that the height of the box is x. There's some information about the length and width. So the length is 9 feet greater than its height. So we're going to take that length and make that x plus 9. It's 9 feet more than whatever the height is. The width is 4 feet less than the height. So we take that height and go down 4, subtract 4 from it. That visual helps us get an idea of how to create a volume function. Now the volume type problems that we're going to stick to are typically box, rectangular, prism type problems. There are several different ones out there, so you may see some cylinder or pyramids, but for our class we're trying to keep this a little bit simpler and focus only on rectangular prisms right now. So if we create a function for the volume, we are creating a function that says length times width times height. And so we're multiplying all of these dimensions together. Now the order that you multiply doesn't really matter because you're just multiplying length and width and height all together. So we have each one of those multiplied. That is a function for the volume. That's one way to write it. Or you can write it in standard form. Now it doesn't say it has to be in standard form, but that is a valid form for a polynomial function. So we could write that out by multiplying and expanding. So if I multiplied this out, maybe I would multiply x minus 4 times x plus 9 first. That would be x times x squared plus 5x minus 36. And then I would distribute the x to get x cubed plus 5x squared minus 36x. Either one of these would be a valid function equation for the volume. In part C, we want to find the dimensions of the box that would give us a volume of 180 cubic feet. So this time we know what the volume is, we have to find what the dimensions will be, and so we're going to solve an equation for x. We're going to substitute 180 in for the volume. Now I'm going to use the factored form equation just for the purpose of showing why it's really not that helpful right now. It is more beneficial to use the standard form equation for this. And that's because when we're solving a polynomial equation, we do want it in factored form, but we want factored form equal to 0. So that I would move that 180 over, and that would subtract 180 from both sides. But here we don't have factored form. We have some factors that are subtracting 180. So that multiplication and subtraction is not factored form. What we would need to do is expand out the factored part. So that factored form looked like this in standard form, x cubed plus 5x squared minus 36x. So if I had expanded that, I would have x cubed plus 5x squared minus 36x minus 180. Now that's an equation that we can solve. It's a polynomial equation, and if we're trying to solve it, we would put it in factored form. Since there are 4 terms here, I'm going to look to see if this can factor by grouping. So we would group the first 2, and I have x cubed plus 5x squared with a GCF of x squared. So it would say x squared times x plus 5. Then we're grouping our second pair. So the last 2 terms, we get negative 36x minus 180. And I'm finding the greatest common factor between those. Now I do know that 2 goes into both of those, but so does 3 or 4 or even 6. So if we're trying to find the greatest common factor, you'll need to look at what divides into both of these, and we would get negative 36 as the greatest. So if I factored out negative 36, we have x plus 5. So that's actually what we want, because we now have a common factor of x plus 5. And so if I wrote this in factored form, it would say 0 equals x plus 5 times x squared minus 36. Now that continues to factor. So that would say 0 equals x plus 5 times, and then if I factor x squared minus 36, that difference of squares would factor into x plus 6 times x minus 6. This is a factored form polynomial equal to 0, so we can use that zero product property and get x equals negative 5, x equals negative 6, and x equals 6. Now if we focus on what is happening here, the x value is representing the height in this situation. There's no way that we can have a height of negative 5. There's no way we can have a height of negative 6. So the only possible height is 6. So when it asks for me to find the dimensions, we already know that the height would be 6 feet. Well, this is a really large plywood box. All right, so then we need the width and the length. We know that the width is 4 feet less than the height, so that would make that width 2 feet. And the length was 9 feet greater than the height, so the length would be 15 feet. Now we have the actual dimensions for this box. In number 4, we're taking a rectangular piece of cardboard and we're going to cut out a square from the corners to create an open top box. Now this one is a little harder to visualize, and if we were in person, I would show you a piece of a cardboard box and we would cut it out. But for now, we're just going to work with the picture. Say I have a sheet of cardboard that is 10 inches longer than it is wide. Well, I have no idea how wide it is, so let's let x be the width. But I do know that the length is 10 inches longer, which would make that x plus 10. What we're going to do is cut a square from each corner. So imagine cutting out a square from every single corner. This is a 4 by 4 inch square. And we're going to do that from every single corner. So we normally just draw these little dotted lines for the corners to show that that is being cut out. We are going to turn that into our box. So when we fold this up, this corner is being cut out, which means that this side is going to fold up together and create the corner of this box. So this 4 by 4 inch square that we've cut out is actually folding up to form this corner here. That means what's left are the length and width here, but that length and width is no longer x and x plus 10. And that's because if I've cut out some of this corner, this x width has subtracted a 4 inch corner on both sides, which is subtracting 8. So that width would be x minus 8. This x plus 10 length has subtracted 4 and 4 on both sides. So if I subtract 8 from x plus 10, I just have x plus 2. This box has folded up to create a 3-dimensional box. As we write a function for this, that volume function is still going to be length times width times height. In this case, that's 4 times x minus 8 times x plus 2. That's a factored form equation. You could write this in standard form, and that would end up being 4x squared minus 24x minus 64. And so I don't expect you to expand all of that in one step. You would need to multiply out x minus 8 times x plus 2 and then distribute the 4. But we should end up with something like this. All right, so for number 5, we're still doing an open box. We're constructing it by cutting out corners again, but this one looks a little bit different. So let's draw a picture of it as well. We have a piece of cardboard that's 20 centimeters by 40 centimeters. So I'm gonna write this 20 by 40. This whole thing is a flat rectangle, and then we're gonna cut out some corners. This time we have no idea how big this corner is. So we're gonna let that be x by x for its corner length and width. We're gonna cut out a corner from every single side. That would fold up to create our open top box. Since that corner is what folds together to create the box's corner, that corner is an x length. So the height of this box would be x. Then we need to know what is the new length and width of this box. It's no longer 20 by 40 because we had to cut out some things. So we cut out a square of x by x on both sides. So this 20 has subtracted x and x, which is minus 2x's. So 20 minus 2x's. And then the length would be 40 minus 2x's. That gives me the dimensions that we have here, and we can create a function for that. So that volume would be length times width times height. Multiplying all three of those together would give me x times 20 minus 2x times 40 minus 2x. There's our general function for the volume. And if we think about the domain of that function, without any context, that's just a polynomial cubic function that's going to have a domain of negative infinity to infinity. But in this context, we need to think about what does that domain actually represent. These are the values of x that work in the function, and there are some limitations to that. Because this x is a distance, it would not make sense for us to have a negative distance that we're cutting out of the box. So automatically, I would know that the domain would be some value 0 to something. But there are other upper limitations as well. There's only so big of a corner that we can create. So if I cut out a 100-inch or 100-centimeter corner, that would not even be possible because I have a 20 by 40 centimeter piece of cardboard. So there are limitations. We just need to figure out what is the upper limitation to that. And so one way that can be helpful is just to know that our sides have to be positive. Our sides are greater than 0. So one side is x, and that just tells me x is greater than 0. Another side is 20 minus 2x. If I set that greater than 0 and solve for x, I would subtract 20, so 2x is greater than negative 20. And when I divide by negative 2, it flips the sign, so x is less than 10. Your other side was 40 minus 2x. If I set that greater than 0, I would still solve for x the same way. Dividing by negative 2 flips the sign, and we get x is less than 20. So right now, we're saying x has to be greater than 0, less than 10, and less than 20. The values of x that work for that would be all the numbers 0 through 10. The last part asked about the maximum volume. So this function, if we were to think about this graphically, it's a cubic function. And we could find the zeros for each one of these factors. The zeros would end up being x equals 0, x equals 10, and x equals 20. This function has an end behavior that is down up. So you could work out what that looks like, but we would sketch a graph and see something like this. That polynomial function does have a maximum. It's a local max. There is a maximum up here. The issue is it's a cubic function, not a quadratic function. And we know how to find the maximum of a cubic, but we don't know how to find the we know how to find the maximum of a quadratic, but we don't know how to find the maximum of a cubic. So I put some asterisks here for this question because we would need to know calculus to be able to solve this equation, or access to a graphing calculator. I could use a graphing tool to figure out where that maximum is. So if we were working this out, we could plug this into Desmos. As we look at Desmos here, we have the function and its modeled volume. We can find where that maximum is. So that maximum is at 4.2 something, and the maximum volume is 1,539.6. So because we don't know the actual maximum without a graphing tool, maybe we would need to be given a graph of this. So if I gave you this information, you hopefully would be able to extract the information from that graph and tell what it would be. So we would say here, the maximum volume would be 1,539.2 cubic centimeters. And we just take that information, create a function that models it, and we use the tools, the algebraic tools that we know to be able to solve. I could not ask you to solve this without having some type of graph given to you because we don't know calculus already. But you will look at these examples again when you get to calculus if you choose to go on that far. All right, so the next is going to look at some surface area type equations.